Today we're starting secondary math 3. So we're going to go slow. You're going to ask questions. You're going to be on top of homework from here on out. Okay, so you've got to do that while staying way on top of secondary math 3 stuff, because the next test will be here and you cannot do bad on the next test. Here we go. So today is 2-1. If you need to take some notes somewhere, that would be great. There's going to be a few things you might want to take notes on, but this video will be posted, so you can go back and watch it. So first of all, just a reminder, standard form of a polynomial is when a polynomial is listed from the highest degree to lowest degree. Now, the coefficient, the number in front of the variable, does not matter. We're only looking at the exponent. So highest exponent to lowest exponent. Standard form also, this is really important, standard form will always have all like terms combined. So highest degree to lowest degree, and then like terms combined. So these are just some examples of some polynomials with in standard form. So everybody look at this one, negative 2x to the 5th plus 4x to the 4th minus 3x cubed plus x squared minus x plus 4. Highest degree to lowest degree. And that's degree 1 and then a constant. Okay, so once again, this is in standard form because we're looking at highest degree to lowest degree. So highest degree to lowest degree. Does everybody see how these are in standard form? Questions about standard form? Okay, so I just wanted to make sure we've got that. Okay, just making sure we know some vocabulary terms. If I say to you terms, I'm talking about the things that are separated by plus and minus signs. So if I say to you, how many terms does a polynomial have? You're going to count how many things we have. Terms are separated by plus and minus signs. And then we talk about degree is the exponent. We're going to be using both of these a lot today, the word terms and degree. So everybody look up here, just look at this example. You don't need to write it down. It's not really anything too difficult here. Just as long as we understand. So just look, this has 3 terms. 1, 2, 3. Terms are separated by plus or minus signs. So you cannot count the plus and minus signs. That would be just 2 terms, but this has 3 terms. Does everybody understand? All right, this has 1, 2 terms. This has 1, 2 terms, and this has 1 term. All right, this is degree 5. The polynomial is degree 5. You go off the highest degree. This is degree 3. This is degree 1. And this would be a constant, degree 0. Okay. So now we're going to have to learn how to name or classify a polynomial. First, before you can name a polynomial, before you can give it an official name, it has to be in standard form, and you have to have all like terms combined. Polynomials have 2 names. Just like we all have 2 names, a first and a last name, polynomials have a first and last name. The first name comes from the highest degree. So looking at this, for example, we would be looking at 4. It's in standard form, all like terms are combined. We would give it a name based on degree 4. You give it its name based on the highest degree. And your second name comes from the number of terms. So in this same polynomial here, we have 1, 2, 3 terms. So its second name would come from the fact that it has 3 terms. So we would name it by degree and then by number of terms. Questions on that? All right, here are the names. So you're going to want to take a picture of this. I don't think we're going to have time for you to write it down. Or if you want to quickly write it down somewhere, you just got to be quick, okay? Because I want you to listen, so quickly take a picture and then I'll explain. So let me move around. Now, I'm going to give you little tips and hints to help you memorize it easier. Okay, so if everybody listens to those, it's going to come much easier. So first of all, the first name comes from the highest degree. If we have degree 0, such as 2, see how there's no x value? Everybody? That's called a constant. There's x to the 0 power, which we know is 1, right? Everybody? So that's called a constant. So if we saw something like 2, we call it a constant. Its first name. If it's degree 1, it's called linear. Look, 2x, this is degree 1. So that would be considered linear. Degree 2 is considered quadratic. Now that makes sense, right, guys? Lines are linear. Degree 1 is a line. Degree 2 is quadratic. Those ones should come natural to us because that's what we focused on the past 2 years of math. Cubic is when it's degree 3. So if it's degree 3, this would be considered cubic. We're not going to say anymore in secondary math 3, we're not going to say degree 3. We're going to say that's a cubic. Okay, and then quartic. Degree 4 is quartic. Here's how I remember. Literally, I think back to this every time. This is just a dumb little thing. But aren't there 4 quarts in a gallon? 4 quarts. So when I see 4, I'm like 4 quarts in a gallon. Oh, yeah. That's quartic. Quarts in a gallon. 4 quarts in a gallon, quartic. And then quintic is degree 5. How I remember this, and you guys are too young for this, but back in the day when I was like young, there was a show on the Disney Channel where this lady had 5 babies. And people actually do in the real world have 5 babies, and that's called having quints. So it was called quints. So that's how I remember. I'm like, oh yeah, that lady that had 5 babies had quints. So quintic is degree 5. So hopefully that will kind of help you remember that, quintic. I always see people write the weirdest things with these because they're kind of weird. I have them like write dinosaur names like polyaptic and all this stuff. So anyways, you'll have to have these memorized correctly. Then after degree 5, there's no special name. So if we have an x to the 6th, it's just 6th degree. X to the 7th, it's just 7th degree. So after degree 5, there's no special name. Does everybody understand? Okay, so then we give it its second name by the number of terms you're going to see. So if you have one term, such as x, that would be considered a monomial. If you have 2 terms, 1, 2, that's considered a binomial. Now you're going to hear me use these throughout secondary 3. I'm going to say we have 2 binomials being multiplied. And if you understand what a binomial is, you're going to understand what I'm saying. So if I said to you now, I have 2 binomials being multiplied, wouldn't that be this times something just like it? 2 binomials being multiplied. A trinomial is if you have 3 terms. So triangles have 3 points, trinomial. Everybody good with that? Trinomial. And then 4 terms has no special name. So after 3 terms, it's just polynomial of 4 terms. So if we have 5 terms, we would say polynomial of 5 terms. Same with 6 terms. Does everybody understand after 3 terms, no special name? So it's just memorizing this chart. So here we go. Let's classify these polynomials. Let's do number 1. So notice, before you can name a polynomial, you first have to write it in standard form, which means all like terms combined, highest degree to lowest degree. So let's do number 1 together. Is just write each polynomial in standard form, then classify the polynomial by degree and by number of terms. So what can we combine here? 4x plus x, which is 5x. I like that I didn't hear 5x squared, right? We're not multiplying these things. That's the only time we add exponents. So 4 apples plus 1 apple is 5 apples. 4x plus 1x is 5x is plus 2. So we have it in standard form, highest degree to lowest degree, and now we can name it. So what degree is this? It's degree 1, right? So it's degree 1. So we would call it linear. Very good. So it's a linear, and then there's how many terms? 2 terms. So that's a binomial. So we would say this is a linear binomial. Does everybody understand? It's not super hard, but you've gotta have that chart down next to you and then memorize it soon, because you don't on the test you're gonna have it memorized. Okay, number 2, let's do another one. It says write each polynomial in standard form, then classify it. So we're gonna combine like terms. Highest degree to lowest degree. So we have positive 3x's minus 3x's. We have 0 x's, correct? So we just have negative 3 left. That is in standard form. So there's no degree, there's no x. It's x to the 0 power technically. So that would be called a constant. Constant. Now there's 1 term. So that's a monomial. So this is a constant monomial. Questions? And just so you guys know, anything that I do on the board for you, with you, you don't have to show work for. You can just watch and then write down the answer. I'm okay with that. Okay, here we go, number 4. So it says put it in standard form, then classify the polynomial. So we know that highest degree to lowest degree and all like terms combined. So my highest degree is s to the 4th. I'm going to write that correctly. It's positive 5s to the 4th. So 5s to the 4th. Then we have a negative 2s. So we'll write minus 2s. And then this is, guys, you got to look from left to right. We read it like a book. So isn't this positive 1 plus 1? I reordered this from highest degree to lowest degree. Now we're going to name it. So it's degree 4, correct? Highest degree is 4. So that's a 4 quarts in a gallon. So this is a quartic. And then there's 1, 2, 3 terms. Triangles have 3 points. Trinomial. Are you guys feeling good about these? Okay. Sweet. Let's do number 5. There's a lot of examples there, so I'll let you practice in just a second. Here we go. So we have 5m squared minus 3m squared. Are those like terms? Yeah, we can combine them. 5 apples minus 3 apples is how many apples? 2 apples. So we have 2m squareds. 5m squareds minus 3m squareds is 2m squareds. We name it by highest degree, so it's quadratic. And there is 1 term, so it's a quadratic monomial. Okay, let's do number 11. There's a couple more. Here we go. So how about I have you try this one on your whiteboard or whatever you want to try it on your paper spine. You answer it, and then I'll have you guys tell me. Ready, set, go. Then I'll let you work. So guys, if we're combining like terms, negative 2x cubed plus 1x cubed is how many x cubed? Negative 1x cubed. You're right. There you go. You fixed it. Then positive 6 minus 4 is positive 2. So those of you that made a sign there somewhere, that's okay. That's why we do this, is to practice. So now we can name it by highest degree. So it's a cubic, and there's 2 terms. So it's a cubic binomial. Everybody feeling good? Okay. Do you want to try this one? Okay, go for it on your whiteboard. So you guys have got it. You're getting it down. Awesome. So you were very good at distributing that. We have x squared plus 5x, correct? Then we're distributing negative 5 through. We got to be really careful, but a lot of you were. Negative 5 times x is negative 5x. Then right here, you did really good to be really careful. Negative 5 times positive 5 is negative 25. We combine all like terms and put it in standard form. So my positive 5x and negative 5x add up to be 0, and we have minus 25. Most of you were able to get there. That's the hardest part. Now naming it, it's degree 2, so that's quadratic. And then 2 terms is binomial. Okay, awesome. Okay, what I'm going to have you do is do problems 1 through 21, and you can check them with me. This is a little bit more difficult, but you got it as long as you're paying attention. I'm going to try to really put it into basic form for you. So we're going to talk about end behavior of a polynomial. So end behavior is what is happening to the far left and to the far right of a graph. So it's happening, okay, end behavior is what's happening at the very ends of a graph. So for example, if I had a quadratic, oops, not writing, this must be my bad pen. Where'd my other pen go? In the laptop. Okay. So if we have a quadratic, the end behavior is what's happening to the far end of the graph. So like over here and over here. And we'll talk about end behavior in context in a minute. If we're looking at a line, we're looking at the far ends of the graph. So we're looking at what's happening here and here. Does everybody understand like when I say end behavior? What I'm just talking about. It's what's happening to the far left and far right of a graph. Oh yeah, okay, just a sec. This is the wrong, oops, just here. Okay. So now that you guys understand that end behavior is what's happening to the far left and far right, we're going to look at some polynomials here. So we have a quadratic right here. We have y is equal to x squared minus x minus 2. What do you notice about the end behavior? It's going this way and this way, correct? So we're looking at the end behavior. All right, now this is another quadratic. Do you see how the end behavior looks the same as the other quadratic? Okay, then if you look right here, this is x to the 4th minus 4x squared plus 4. Well, look at the end behavior. Isn't it behaving the same as the quadratic? Right? Okay, and then if you look down here, this is another x to the 4th, but it's negative x to the 4th. We have our end behavior happening over here and over here. So notice it's going down and down. And then over here we have a quadratic. And you see how the end behavior is working the same. Okay, so here's the general rule. Are you ready to learn the general rule? For even. This is degree 2, this was degree 2, this was degree 4, this was degree 4, this was degree 2. Does everybody understand how those are all even degrees? Even degree polynomials will have either the same end behavior, either up and up or down and down. Do you see what I mean by the same? Up and up or down and down. What causes the end behavior is the highest degree, and if it's even, and then you'll look at the leading coefficient. If it's positive, it'll be up and up. If it's negative, that negative takes and flips it upside down. That's when it's down and down. So everybody look up here. We have y is equal to x squared minus x minus 2. It's an even degree, so it has the same end behavior. It's a positive in front of the highest degree, so it'd be up and up, like a smiley face. Positive people like to smile. Okay, let's look at this one. So this is a quadratic. We have degree 2, correct? And isn't positive 2 a positive? So that's up and up. Just like positive people like to smile. Questions on that? So right here we have degree 4. Isn't degree 4 even? So we know it's end behavior up and up or down and down. Now you look in front. Was it positive? Yes. So this is a smiley face. Up and up. Everybody good with that? So right here, this is degree 4. So it has end behavior that's the same. We know it's up and up or down and down. Now it's negative in front. Now negative flips it upside down, so that's going to make it down and down. Negative people like to frown. So do you see how it flips it upside down, making it a frowny face? So we have an even degree right here, a quadratic, and it's negative in front. Negative people like to frown, so it's down and down. Does everybody see how that works? So if I gave you degree 6, and it was negative 2, x to the 6, isn't that an even degree? So we would say it's either up and up or down and down. It's a negative in front, so it's going to be down and down. Does everybody understand? Okay, awesome. So that rule was written right there for you, in case you needed it. Okay. Okay, end behavior with odd behaviors. So odd degrees. So everybody look right here. We have function x cubed minus x squared minus 3. Notice the end behavior is opposite. You see how it's opposite end behavior? Not the same, opposite end behavior. We have y is equal to 2x plus 1. Do you see how this is opposite end behavior? Opposite, not the same, opposite end behavior. So right here we have another one with opposite end behavior. And we have another one with degree 3 with opposite end behavior. So it's going to work the same as evens, but a little bit differently. So an odd degree function has opposite end behavior. Odd, opposite end behavior. Then if it's positive in front, such as this, it's going to be down and up. So from left to right, we look at end behavior. You see how it's down and up? Everybody? That would be considered down and up. Now over here, we have a degree 1, which is odd, correct? So we have opposite end behavior. Now it's a positive in front. That's down and up. Now look, let's make sense of this so that we don't have to memorize anything. Isn't this a positive line? Well, that's going to happen because we have a positive slope. So end behavior will work the same for something like a cubic. So it doesn't matter what's happening in between. It's going to work, the end behavior is going to work like a line. So it's degree 3, so it has opposite end behavior. It's positive in front, so it's going to have the same end behavior as a line. That's positive. You see how this is a positive line? So do you see how it was down and up, just like this? Okay. Right here, notice we have like a negative line, correct? That's an odd degree. So it has opposite end behavior, and a negative line looks like this. So from left to right, that's considered up and down. Do you see how it's up and down? Everybody good? Okay? So we look over here, we have x cubed. Okay, that's an odd degree. So we say we have opposite end behavior, and now it's a negative in front. So that's going to behave, the end behavior is going to behave like a line that's negative. So I draw in a negative line just so I can see. So it's going to be up and down. You see how it's up and down? Doesn't look the same in between, but we're talking end behavior. You see how you can use lines and quadratics to kind of work in your advantage. Okay. Do we have questions on this? Okay, let's just practice a few then. Oh yeah, Okay, now let's just get right into it. So if you can see that it's up and up or down and down, that's great. Now we also have to be able to say it in, I call it calculus notation. So everybody look up here so you can make sense of this. If we have this function, here's our x-axis, correct? Everybody? This is our x-axis. If I walk this way forever, won't I eventually get to positive infinity? I'm approaching positive infinity. If I kept walking this way forever on the x-axis, aren't I going to get larger and larger and larger? Okay, if I walk this way on the x-axis, if I walk in the negative direction forever, aren't I going to approach negative infinity? Okay, awesome. So we understand that that's x. Now I'm going to do y. If I go upward forever, let's change colors here, come on. If I walk upward forever on y, aren't I eventually going to approach positive infinity? Now if I walk downwards on y, won't I approach negative infinity? Okay. So we're going to state end behavior. We know this one is up and up, correct? Up and up. Okay. So we have to state it like this. So as x is approaching positive infinity, so as x is going this way, where's your function approaching? So as x gets larger and larger, as x approaches positive infinity, isn't our function approaching positive infinity on the y? So we would write positive infinity. So then we're going to answer this. As x approaches negative infinity, so as x gets smaller and smaller, where's your function approaching? So as x gets smaller and smaller, isn't our function growing up to positive infinity? So we'd write positive infinity. You've just done some calculus. Do we have questions on that? This is what's important. We're going to do more examples. This is what's important. If you're not seeing it, though, then you need to ask. As x gets smaller and smaller, isn't our function growing to positive infinity? As x approaches negative infinity, our function is approaching positive infinity. Okay. Because the function's not growing down to negative infinity. It's growing to positive infinity. Good question. So that's what we're going to do right here. Here we go. So this is an down and down. Look, it's even and it's negative. It's down and down end behavior, right? So everybody, as x approaches positive infinity, where's your function approaching? Negative infinity. Does everybody understand? As x, this is the x-axis, guys. As x is approaching negative infinity, where's your function growing to? Negative infinity, right? Isn't it going down? As these get smaller and smaller, it's going down to negative infinity. All right. Questions on that? Okay, let's do some odd degrees. So let's look right here. This is an example of down and up. So everybody, as x approaches positive infinity, where's f of x growing to? Where's your function growing to? Positive infinity. As x is growing to negative infinity, where's the function growing to? Negative infinity. Are we all seeing it? Okay, let's do this one. It's an odd degree. It's negative, so it's up and down, just like a negative facing line. So as x is approaching positive infinity, where's my function approaching? Negative infinity. As x is approaching negative infinity, where's my function growing? Positive infinity. Okay, awesome. Okay, sweet. Let's do number 22 together. Here we go. So it says, determine the end behavior of the graph of each polynomial function. We need to be able to do this without a calculator because there's going to be times that I give you one that is not going to be graphable. So we're going to use all our rules. Here we go. This is degree 4, so it's even, correct? So then you'd say evens have either up and up or down and down. Is it a positive? Yeah. So then it's a smiley face, correct? Yeah. It's not quadratic, but won't the end behavior for all evens work like a quadratic? Yeah. So all we need to know is it looks like this, the end behavior. So right now, I'm going to write it as up and up. Any questions on how we got up and up? Okay, so now we have to write it in calculus notation. This is the important thing in secondary math 3. So the up and up is great. But now we have to write it as, feel right, as x approaches positive infinity. So as our x is growing this way forever, where's our function growing to? Where's f of x approaching? Positive infinity. Do you see how it's growing up? Function's growing up as x is growing that way. then you'd say as x approaches negative infinity, so as x is approaching negative infinity, where's your function growing to? Positive infinity. Our function f of x is growing to positive infinity. And we've answered the problem. We all seeing it? We're all feeling good? Okay, write down that answer. And we'll do another one. So once again, this is not a quadratic, but the end behavior works like a quadratic because a quadratic is an even function. So let's do 23. Okay, we got to be careful on 23 because it's not in standard form. So we're going to rewrite it real quick as positive 5x squared minus 3x cubed. Nope, I should have put the cubed first, right? So I thought that was my eraser. Here we go. Let's rewrite it correctly. So you have negative 3x cubed plus 5x squared, and then plus 50. Okay, we're not going to graph it. We're going to use our rules because it's much quicker, really. So we say, okay, it's an odd degree, so it has opposite end behavior. Now it's a negative, correct? So it's going to behave like a negative line. So I draw in a negative line. From left to right, isn't that up and down? Do we have questions? So it's up and down. So then we'll say, okay, as x is approaching positive infinity, where's our function growing to? F of x is approaching negative infinity, right? Isn't it growing down as x is getting larger and larger? It's going down to negative infinity. Okay, and then as x approaches negative infinity, so as x is getting smaller and smaller, where's my function growing to? Positive infinity. So f of x is growing to positive infinity. Do we have questions? Okay. Good. Maybe one more, and then I'll let you work. Here we go. One more, then I'll let you work. Let's do 29. First thing we need to do is put it in standard form. So we're going to rewrite it as negative 5x to the 6th, and then minus 11x cubed, plus 3x, and then plus 20. And now we're going to determine our end behavior. So you only need to look at the leading coefficient here. It's 6, so it's even. So we want to have the same end behavior. Up and up or down and down. It's a negative in front, so I want to be down and down. So like a quadratic, even though it's not quadratic, the end behavior will work the same. So we'd say down and down. So now we would write it in calculus notation as x approaches positive infinity, f of x approaches, so guys look, as x is approaching positive infinity, where's your function growing to? Negative infinity. As x approaches negative infinity, f of x is approaching negative infinity. Are we all understanding it? Okay, perfect. We'll go back to turning points in a minute. So I want you to do the end behavior of 22 through 30. Ready, set, go. Turning points. So everybody look up here real quick. So I'm going to try to help this make sense for you. Even degrees, we're going to talk about how many turning points you're going to see them have. So a quadratic always has one turning point. Think about it, guys. A quadratic always has one turning point. Aren't quadratics symmetric over an axis of symmetry? Guys, so we have this symmetric parabola. It's coming down. It's going to turn and go back up. Aren't all parabolas U-shapes? So quadratics always have one turning point. Notice, degree 2 is a quadratic. It had one turning point. That's one less than the degree. 1 is 1 less than 2, correct? So the number of turning points a quadratic had was 1 less than the degree. Do you understand what I'm saying? Okay, so look at this. It's a quadratic. It had one turning point, and that's degree 2. 1 less than that is 1. We had one turning point. Now look up here. This is degree 4. Do you see how degree 4 comes down? There's a turning point, goes up. There's a turning point, goes down. There's a turning point. There are 3 turning points in degree 4. Do you see that degree 4? 1 less than that is 3. Just like with degree 2, 1 less than that was 1, correct? So do you see how there is one less turning point than there is degree? Is everybody good with that? So degree 5 could have 4 turning points, correct? The most number, degree 5 would have 4 turning points, right? 1 less than that, do you get what I'm saying? Okay, so look right here though, this is interesting. This is a 4th degree that goes up. It's increasing, still increasing, still increasing, till there. Now that one only had 1 turning point, right? So degree 4 can have 4, so degree 4 can have 3 turning points or 1 turning point. Notice it went down in 2s. Do you see what I'm saying? So degree 4 could have 3 turning points. What's 2 less than that? 1 turning point. So degree 4s can have at most 3 turning points, but it might have less. But it can't have 2. It could have 3. It could have 1 turning point. Flipping you off over there on accident. Sorry. Does everybody understand what I'm saying? Blustering me up here. Yes. Great question. So 6 will either have, so 6 degree will have 1 less than that at most, 5 turning points. It could also have 3 turning points, 2 less than that, or 1 turning point. What? It just, okay, because odd turning points will work the same. So like, I'll tell you an example. So here was a 4th degree, right, that only had 1 turning point. It doesn't always necessarily have 3. Does that make sense? So it can't have 2 because we're talking evens. So here's how I like to say it in honors. I like to tell them, okay, my evens are degree, like for example, degree 6, degree 4, degree 2, correct? Okay, so how many turning points at most could 6 have? 5. At most, how many could degree 4 have? 3. And at most, how many could degree 2 have? 1. So a degree 6 could have 5 turning points, 3, or 1. Yes. The same as all the other evens. Does that help a little bit? So degree 8, yep, it could have 5 at most, or it could have 3, or it could have 1 turning point. It just depends on the polynomial. Like this 4th happened to have 1 turning point, where this 4th had 3. Some 4ths have 3, some 4ths have 1. Okay, so let's talk about that. I mean, the same thing happens for odd. So everybody look right here. This is a degree 3. Now look, we're increasing. I'm going to start with a different degree 3, this one. Don't we have 1, 2 turning points? 3, 1 less than that is 2, correct? 2. Now let's look at another degree 3, right here. This one is increasing. It slows down, but it keeps increasing. So it was strictly increasing. This one had no turning points, 0. Now look at a line. Doesn't a line have no turning points? Doesn't a line have no turning points? So this will work like a even. So if we have an x to the, let's go big, 7, x to the 5th, x to the 3rd, x to the 1st. So degree 7 could have at most 6 turning points, correct? 1 less than that. Degree 5 could have 4. Degree 3 could have 2. And degree 1 will have 0 turning points. So that means a polynomial of degree 7 could have at most 6, but it could have 4 turning points, or it could have 2 turning points, or it could have no turning points. Does that help everybody a little bit see it better? Yes. This is just the max number of turning points, but there are 7th degree polynomials with only 4 turning points. There are 7th degree polynomials with only 2. There are 7th degrees with only 0 turning points. It would be a strictly increasing or decreasing function. Okay, so I want us to now go through and say how many turning points at most it could have, and then here we go. And then we'll count down. So on number 22, what's the most number of turning points we could have? 3. Now, degree 4, if you need to write it out, so we know degree 4, and then after that's degree 2, correct? So this one is 3, this one is 1. So 3 is the most number of turning points, but it could have 3 or 1 turning points. Does everybody understand? Just like that 1/4 degree that had 1 turning point a minute ago. We're all good with that? Okay, let's do this one. Number 23. We have it in standard forms. It's a degree 3, so it can have at most how many turning points? 2, or it could have 0 turning points. So 2 was at most. But it might have 0 turning points. Once again, there are cubics that look like this. Doesn't that one have no turning points? It slows down, but it never turns. It's always decreasing. Okay. All right, so looking at this one, it's degree 6, so it could have at most 5 turning points, right? And then we could have 3 or 1 turning point. Just depends on the polynomial. Okay, awesome. You guys understand it. So what I'm going to have you do is 22 through 30, write in the max number of turning points it could have, and then the rest of the turning points it could have. Ready, set, go. Quickly. So this is what I just said a second ago, but I didn't give you this. So here's the rule. Once again, that's just a polynomial will have at most n minus 1 turning points. That just means 1 less than the degree, and then it works in twos. So we already know that 1 has no turning points, 2 has 1 turning point, 3 has 2 or none, 4 has 3 or 1, working in twos. So we understand that. That's just the rule. Okay, so what I want you to do is 22 through 30. So state the most number of turning points it could have, then state how many it actually has. So what you're going to do is you're going to state the most number it has, then you're going to graph it and look at it, and then see how many it has. So everybody, let's look at number 31 together. It's x cubed plus 4x. What's the most number of turning points we could have? 2 at most, correct? Everybody? But couldn't we have 0? 0. So 2 at most or 0 turning points. So now pull up your graphing calculator real quick and type it in. X cubed plus 4x. And then look and see how many it actually has. Yes. Let me look. So x cubed plus 4x, and we hit graph. And you might have to change your window. Okay, I'm going to change my window. Look at my calculator. I can't really see very good, so I'm going to change my window. Don't I need to see higher up on the y? Guys? So I go to window. Like, I can't see very high up. I go to window. I'm going to go to y max. That's the only one I need to change. I'm going to make it bigger than 5. I'm going to just go like 20 and then graph it again. Now, can't I see that there are no turning points on this? It's strictly increasing. Do you see how it's strictly increasing? Just going up forever? Okay, so we would say actual number of turning points is none. So this one had no turning points. Okay, so do 32 and 33. Confident. Okay, so number 22, we don't need to do. Okay, awesome. Okay, so now I'm going to teach you one new thing. Last thing for the day. So last new thing. We can determine a degree, that means the highest exponent of a polynomial, by looking at our y values. So guys, everybody, every polynomial has a set of xy points, correct? Yeah. If we can have a function, then that's just a bunch of xy points being plotted and connected. Do you all understand that? Okay, awesome. So if we have an xy chart here, we can determine the degree of a polynomial. Now, one thing has to be true. Our x values have to be changing by the same amount. Do you see how these are all changing by 1? -2, 1, -1, 0, 1, 2, 3. They're all going up in ones. So that's the only rule. Our x values have to be changing by 1 every time. Okay, so they are. So what you're going to do is you're going to take and subtract your y values. But you've got to, here's the rule. You've got to subtract your y value that comes before the y value above it. So we're going to very carefully do -1. You see I'm starting with the y value that comes before the y value above it? -1 minus -3. Type it in your calculator. You cannot make errors with this or it's just going to hurt you. -1, this value, minus this value. So we're doing -1 minus -3. What do we get? You should get 2. It's -1 minus -3. Now we're going to take the differences between these two y values. You have to do this y value minus the y value that comes before it. 1 minus -1, which is, no, Be very careful. That's why these are hard for people, because people make errors with subtraction. Guys, it's 1 minus -1. 2, awesome. 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. So we took differences the first time and got something the same, correct? So this would be considered degree 1. So whenever the differences are the same, that's when you know that that's the degree. So this is degree 1, so this is linear. Do you see how they were the same after we took differences the first time? Yeah. Don't make the mistake on my honors test, I had people say degree 2 because the differences were 2. It's not, the differences don't matter. It's just when they're the same. So if these would have all come out to be 3, it still would have been linear. Does that make sense? Okay, let's do this next one. So we're going to take differences of the y values. So I'm going to draw in my little things, being very careful not to miss any. 0, you have to start with the y value that comes before the y value above it. 0 minus -2. 2. -2 minus 0. -2. -8 minus -2. -6. If you need to type it into your calculator, do it. -18 minus -8. -10. Were they the same when we took differences the first time? No. So we're going to take differences again with these new values. So we're going to do this. Now here's the catch. You've got to take, just like we did 0 minus -2, you've got to do -2 minus this value. You've got to take this value, subtract the value that comes before it, just like we did right here. -2 minus -2. 0. -6 minus -2. -4 and -10 minus -6. Oh, no, wait. Did I mess this one up? Wait, I made this problem up, but I thought I was good. No, we're still good. Okay, we know we've done our math right. -10 minus -6. -4, were they the same everywhere? No. So it was not degree 2. So we're going to take differences again. -4 minus 0. -4. -4 minus -4. 0. So we were never able to find a difference that was the same, correct? So it's not degree 3. Now, if we did it again, we'd only get one value. So this one has no polynomial matches the function. So you would say there's no polynomial that matches the function. Like this is just a bunch of random points. Does that make sense? Because there was no difference that was the same. No polynomial that matches. Does everybody understand though? If the differences would have come out the same right here, it would have been quadratic. Yes? Okay, I forgot that I did do that one on purpose so that I could show you that, because that does happen. Okay, be really careful though. Okay, what I want you to do is 34, 35, and then 40. It's just all the same thing that we just did. Ready, set, go. Check those with me once you've done them. You guys be really careful with subtraction, because if you make one teeny error, the whole thing's done. You have to start completely over. If you make one little error with subtraction. It's thinking more advancedly now, thinking a little differently. That's what we've got to be able to do in secondary math 3, is take something that we've learned and apply it a little differently. So it says, given the picture of these graphs, they're not the exact same as yours, because I'm going to make you practice them before we leave. We're going to determine the sign of the leading coefficient and the degree of the polynomial function for each graph. So what I want you to remember is for end behavior, don't we just look at the leading term, correct? Everybody? Are we paying attention? This is going to be on your test. So to determine end behavior, we look at the leading term, the highest degree, correct? Okay, so we see that this is up and up, correct? So doesn't that mean that it was an even degree? Okay, so we know it's even. I'm just going to kind of process of elimination here. Now, it was even and it's up and up. So doesn't that mean that the leading coefficient was positive? Right? So a positive in front of the x. Now we don't know what the number was in front, but I just want to know, is it positive or negative? So we've just determined the sign in front of it, but we don't know what degree it is. We just know it's even. Is it degree 2? No, don't quadratics have one turning point and they're symmetric? There's 1, 2, 3 turning points. There's 3 turning points. Don't we know that there's always one less turning point than degree? So this is degree 4. Do you see how I did that? We're going backwards. So look right here. This has opposite end behavior, so won't it be odd? The exponent. Guys? Now it's down and up, so a line that looks like down and up, that's a positive line, right? Everybody? Yeah. So it must be positive in front. Now it's not a line, and it has 1, 2 turning points, so it must be degree 3, correct? 3? If there's 2 turning points, there's 1 more degree than that, right? So what about these ones? We see it's down and down, so won't it be even? Yes. And it's a negative in front, correct? Yep. So we know it's negative x something, or negative something, negative 2x or whatever. So we know, and then there's 1, 2, 3, 4, 5 turning points, so it must be degree 6. Okay, so this one is up and down. There is no turning point. Well, it's opposite end behavior, so it's odd. Now it looks like the same end behavior as a negative line. So we have a negative in front. Who? Sorry? Okay, thanks. So then it's not degree 1, correct? Our lines have the same slope. So it must be degree 3. Does everybody see how I thought through that? Okay. So I want you to go ahead and try, well, what if you saw something like this? It was definitely not quadratic, correct? But only has 1 turning point. So we wouldn't say degree 2 though, but can a degree 4 also have 1 turning point? Okay, so this would be a positive x to the 4th. Okay, we understand it. Okay, how about you finish up 36 through 38, 39. Yep, that's what I want you to do. That's where we're going to end, 36 through 39. And the rest, and then you did 40. So we don't have to do that bottom part, 41 through 46. You could if you wanted more practice, but you've got to be able to simplify those correctly. So I'm not requiring 41 through 46. If you want to cross those out now, you can. But I bet you can finish this up in class. So check 36 to 38 with me. You have 4 minutes to do that.